Hi there, Frank here. Today I'm going to be talking about the Laplace transform and how to use it to solve circuits. So let's first thing first, let's draw our circuit. The circuit is going to be like this. Then we're going to have a resistance. Then we're going to have an inductance. And then we're going to have a capacitor. And then that's it. Here it is going to be a switch like this. It's going to be closed. T equals 0. I'm going to comment that in a little bit. Okay, there we go. So let's suppose that the current is flowing this way. This IT. We have 10 ohm, 1 Henry, 1/9 of farad, plus minus, and this over R. Here's our L. Okay, so basically what it's saying is that in the circuit the switch is open for T. Let's write it down. So it's the switch is open for T less than 0 and is closed for T equals 0. So let's suppose that C, so basically VC 0 minus, I'm gonna explain that why 8 volts. Find IT for T greater than 0. Okay, so to solve this, we're gonna use the Laplace transform. But before I get into the details of the Laplace transform, I'm gonna write toolbox like here in the right hand side, on the right hand side. This toolbox is going to be useful to understand what the Laplace transform is used for before we get into this problem. So this is like one of the problems you might find in your electrical engineering class. So let me just write our toolbox. Like we need the right tools. So for the current, we have V equal R times I t, right? So if I apply the Laplace transform to this, I will get V naught S equal to R times I naught S. Now for the inductance, we have Vt equal to L di dt. So if you apply and we do the Laplace transform of this, we will get V naught S L times S I S minus I, oh whoops, 0 minus. For the capacitor, we have IT equal to C dV dt. So applying the Laplace transform to this, we would have I S equal to C times SVS minus V0 minus, which we can rewrite as Vs equal to 1 over SC times IS plus V0 minus over S. Now, this is actually the toolbox that we're gonna keep in mind before we actually start solving the problem. Okay, this is just a toolbox. Now let's start to solve the problem. So basically what this problem is saying is that the switch is actually open for t less than 0, so and is closed for t equals 0. So the moment t equals 0, the switch closes like this. And then it's gonna give us VC 0 minus blah blah blah. Okay, so what this is actually saying is that for our problem, I 0 minus is equal to 0, because you know it's pretty straightforward. We just said that t is left for t less than 0, the switch is open. So since the switch is open, and we need a closed circuit in order for the current to circulate, you know, there's not going to be current. So we know that I of 0 minus is going to be equal to 0, so there is no current flowing because, you know, the circuit is open. Now we also know that V of 0 minus is 8 volts. We know that because you know, the problem is just giving this value to us. Now what we're gonna do is to write the Laplace equivalent circuit. So what this actually means is that we're gonna write another circuit like this one, but it's gonna be equivalent, which is gonna be equivalent to the one we just, you know, draw, but it's gonna be the Laplace one, and we're gonna work on that. It's like when you were doing the Thevenin equivalent circuit, but this time we're gonna do it for Laplace, so which is different. So in our Laplace circuit, we can think about the capacitor, which is, just before that, before drawing the new circuit, we have to keep in mind that once the switch is closed, there's gonna be current flowing, but there is no generator. So we are just assuming that the capacitor is charged, and it just, is starting to is discharging, and therefore the current is gonna flow, and it's gonna pass through the resistance and the inductance, and until the capacitor is gonna be fully discharged. Okay, so we can actually think in the Laplace equivalent circuit, we can actually think about the capacitor as a resistance plus a difference of potential. So basically, resistance plus a power source. And then we can think about our inductance as a resistance, and our resistance is just going to be, a resistance. It's just going to stay the way it is. So if we draw our equivalent circuit, we're basically going to get something like this. I still going to be, the current is still going to flow the same way. The resistance is still gonna be a resistance. Then our inductance is gonna be a resistance. I'm gonna write it like this, only because it's an equivalent circuit. And our capacitor is gonna become resistance plus a power source, which is going to give us a difference of potential. So I got a resistance and a power source like this, and then that's it. Okay, so the resistance is still going to be 10 ohm, as it's given by the problem. So this is going to be our inductance as, and since it was one array, we are also going to have one S. Now we had the capacitor with a resistance of 1/9 of farad. So this is going to be 9 over S. And then we have the power source, which is still a capacitor, but which is 8 volt. So it's actually gonna be 8 over S. Okay, so we know that the sum of all the currents is gonna be equal to 0, so we can just write them down here. So we basically have 10 IS plus SIS plus 9 over S IS, of course, plus 8 over S equal to 0. So we just basically said, okay, so the sum of all these guys is going to be equal to 0 is just one of the fundamental theorems of electrical engineering, of course. So basically 10, our resistance, plus 1, I just wrote SIS because just, one S is S, plus 9 over S, so our so resistance, inductance, and which is a resistance in the equivalent circuit. This which was the capacitor, which is now a resistance, plus 8 over S, which is the generator, which used to be the capacitor. We just split the capacitor. All these is going to be equal to 0. Okay, so if this is true, and it is true, of course, then we can say that IS is actually, whoops, well, we can just get IS in front of everything, and then rewrite all those guys together, and then plus 8 over S. So let's do it. So we actually put is in front of everything, so we multiply by is, we get, what do we get? Well, we get 10 plus s plus 9 over s, and then plus this guy here, 8 over s. Everything equal to 0. Okay, so let's go on, and we get is. Well, is times 10s plus s squared plus 9 over s. All these is going to be plus 8 over s equal to 0. So I just did the I just basically, you know, got rid of the fraction because I had an s here, so I basically multiply all those other two guys by s. Okay, and so our last step to find is, well, we just have those guys, so we basically gonna flip. So we get, what do we get? Well, we get negative 8 over s squared plus 10s plus 9. Okay. So what do we have is is, but it's not over, it barely just started, because now we have to apply the Laplace transform. In order to apply to the Laplace transform, there are a few things we have to keep in mind as we have this. First of all, I have to find the roots of this polynomial, and you can do delta. It's fine if you do the delta of s squared plus 10s plus 9, but it's also boring and it takes you a little bit of time. You can see that in order to get this, you can use you can actually have the roots. Well, let's just write it down properly. Okay, so let's find the roots. So the roots of s squared plus 10s plus 9 are s equal to -1 and s equal to -9. Because, you know, if you do the delta, you basically get you will basically get those two values. It's easy to check. You can basically multiply and find out that you get that. So we will basically have a negative, and you're gonna put the negative sign in front of everything just to get rid of it, of 8 over s plus 1 times s plus 9, because those two are the roots. So in order to find the poles, we're basically gonna do a clever trick. We're gonna multiply this whole thing by s, well, the numerator by s plus 1, and then we're gonna substitute s with the value of our first root. Okay, so let's just do that. Okay, so in order to find the first pole, the pole are gonna be 2. Okay, so in order to find our first pole, we're just gonna rewrite this. Okay, so s plus 1 times s plus 9, but we're gonna have 8 that multiplies this guy here. So we're gonna multiply by this guy here, s plus 1. Okay, so it's actually pretty straightforward that those two guys are gonna cancel out. And we will get negative in front of everything, 8 over s plus 9. Okay, so now we're gonna substitute these s here with the first root that we have found, so -1. So what we are gonna get is -8 over -1 plus 9, which is actually gonna gonna give us negative in front of everything, 8 over, well, negative 1 plus 9 is 8, of course, positive 8, so those two guys cancel out, is 1 over 1, so it's negative 1. So why is this important? Well, we're gonna see it in a little bit. Let's find the other pole. So in order to find the other pole, we're gonna have 8 over 8 times the other, so s plus 9, everything over those two guys, so s plus 1 times s plus 9. So those two guys cancel out, and we're gonna get negative in front of everything, 8 over s plus 1. And now we're gonna substitute the other value of s we have found. So this is gonna give us negative 8 of negative 9 plus 1, which is negative 8 over negative 1 plus 1 is negative 8. So negative and a negative, those two guys cancel out, but negative and negative is going to be a positive 1. So negative 1, positive 1. Okay, now we have everything we need to write the Laplace transform. But in this case, we have basically found is, if you remember, and we have used this in order to, so that we can write the Laplace transform. But in this case, we're going to use the anti-transform because we need it. The problem was just asking us to find it. So basically, we're going to have it equal to the Laplace transform to the negative 1, so the anti-transform of is, which is this guy here that we had just found. So it is actually going to be equal to, well, the Laplace transform inverse, so the anti-transform of Laplace of this guy here. So negative 8 over s squared plus 10s plus 9. So it is going to be equal to, okay, so we're going to have a negative in front of everything because of this guy here, so we start with a negative. So if you remember, the Laplace transform and the anti-transform is going to be elevated to the power of t of something. So let's crack on. We have a negative which comes from this guy here, so negative e raised to the power of our root, the root that we just found. So negative 1 times t, so negative t. Then we're going to have a plus, because the second one that we have just found is positive, so plus. And we're going to have e raised to the power of our other root, so negative 9 times t, which gives negative 9t. Negative 9t. And this is basically it. This is the anti-transform of Laplace with which we have just found I of t. So a quick recap. The idea here is to basically get you basically get a circuit and you draw the equivalent circuit in which the resistance is still a resistance, the inductance becomes a resistance, and the capacitor is split between resistance and a power source and a power supply. Please note that this is only because in this very example, the capacitor is charged, there is no other power supply, and the switch is closed. So if it wasn't, like if it was just a normal capacitor with an existing power source, and therefore it was not charged, was discharged, then we wouldn't have wrote it this way. We would then just wrote the resistance. It depends, but this way. So you basically get the 10 ohm. We can write it in terms of S, which is just 10 S. The inductance, whatever you have, like 1 Henry, 2 Henry, 3 Henry, 4 Henry, whatever, you get 4, 1, 2, 3, 4, 5, and so on in front of S. So it becomes 1S, 2S, 3S, 4S, and so on. This one for the capacitor, if you have like a fraction like we have here, you can have to flip and then put S at the denominator. Like if you have 1 over 8, it will become 8 over S. If you have, I don't know, 1 over 2, it will become 2 over S, and so on. And you do the same for the power supply. So basically, well, no, you do, the power supply is going to be over S. Then we use the property that the sum of all those currents is going to be equal to 0. And then we found I of S. When you find out I of S, you can use the Laplace transform, as we wrote everything in terms of S. And thanks to the Laplace Anti-Transform, which goes from I of S, so everything wrote in terms of S, to I of t, which is the one that the problem was asking for, you basically can solve the problem. But in order to do that, you have to find the roots. You can do by delta or by any way you want. You just have to find the two roots, so the 2s of the, in this case, the denominator. And then once you find them, you basically you do a clever trick to find the poles, which are very important, which is to multiply the numerator by the first, and also multiply the numerator by the second, and then substitute the first one, the first as we have found, and the second as that we have found. And you get the two values, and then you can just apply the inverse transform, the inverse Laplace transform, in order to get I of t. I'm gonna be doing more examples, but for now this is pretty much it.